Welcome. So, we have analyzed the nature of the fields, electric field and magnetic fields radiated by a current element in the last class. Now, we will see that what is the proof that radiation is taking place. So, we look at the expression of E far field and H far field at a distance from the antenna, these are dominating. So, other fields are negligible there. So, we write there. Now, we will have to take the pointing vector you know E cross H star. So, we will have to take this in spherical coordinate, that means AR, A theta, A phi, this all you know, just if any of you forgot, that is why I am writing ER, E theta, E phi and HR star, H theta star, H phi star, but you know that in our case we do not have this, we do not have this, we do not have these. So, these are zeros here and you can find this expression. So, you can find that E cross H star, that will be having a radial component So, this will be the expression. Now, again if you look at, you have all these expressions, just look at them. ER H phi star, that actually is a purely imaginary term. So, in the pointing vector it is present, but we know the time average power density is given by S phasor SAV, that is half real E cross H star. So, that will not give any time average power flow, that is only local power there. So, that is nothing but only AR. So, it has only a radial component, that means time average power is flowing only in the radial direction. It is not flowing in any other direction. That means, I have the current element here, this is my current element, in this direction it is going in this direction. So, all radial directions it is flowing out, but in no other direction it is flowing. So, if I look from here, it is flowing here, if I look from here, it is flowing here, but do not assume that just because I have drawn arrows means it is equally flowing. I have said that no real antenna can radiate equally. Similarly, all directions that we will see just now, that there is a shape of that, but it is having radiation, power is flowing out. So, this is the proof that it is getting radiated. Now, let us complete that, because we know the fields. So, we can write what is the expression for that. If you do that, you will be able to write it in this eta naught by 8 dl by lambda naught whole square I square sin square theta by R square AR watts per meter square. So, this is the expression. So, the power flow, that means the radiation from this antenna, that depends on this intrinsic impedance, you know, it is 377 ohm or 120 pi. So, in that terms it can be also said that 15 pi etcetera. This it depends on the size of the current element, infinitesimal by lambda naught. Now, in practical cases, if I dl by lambda naught, suppose I have a 1 centimeter antenna, but my wavelength is, let us say, 100 meters etcetera. So, that we can consider as infinitesimal. So, current elements are used. Then it depends obviously on the source strength, how much current I am giving. Then it has a distribution, power distribution varies as sin square theta, that we will see, and also it is inversely proportional to R square, because S average is nothing but E cross H. E in the far field depends on 1 by R, H also in the far field depend in 1 by R. So, their product, that is natural, it is dependent on R square. That is why we say that power, these are all inverse square of power, but remember that fields there 1 by R variation. And so, this clearly says that this radiation is taking place. Now, instead of going here, you can do an exercise that I have found it from the actual expressions derived, but this S average power can also be obtained from only far field components. So, if I find half real E far field cross H far field star, that also would give me this same value. So, it also shows that actually far fields are important because they are carrying power. Other components, those induction fields, electrostatic fields, they are effective locally, but they do not represent radiation of power. They actually represent local storage, because they are, if you do this E cross H star business there, then you will see that they actually give rise to reactive power. Reactive power does not flow, but real power flow, that is contributed by far field. That is why from the very beginning we have separated them. That means, at a certain distance from the antenna, whatever fields dominate, they are actually important, they carry power, others do not carry any power. So, far fields are the vehicle for transportation of energy. So, now we can say that why inductive fields are called inductive fields. Initially I could not tell it, but now I can say that if you take inductive field terms E and H, inductive field terms, electric field and magnetic fields, do this Poynting vector business, then you will find that they give rise to a J component. Now, that is plus J. So, that is why it is called inductive, and if it turns out to be minus J, it becomes negative. Usually it is an plus J component of power, that is why they are called inductive fields, as if in an inductor there is a locally storage of energy. That energy does not flow in a typical circuit also. So, here also near the antenna there is a energy storage, but that energy is not flowing. Only after certain distance that energy starts flowing. Okay. And now it is, we can also find out, you see all these are constants. So, at a particular distance r, the radiated power that has a sin square theta type variation. So, we can plot S, this magnitude of this, if we plot. So, suppose what we will do, that we have x, y, z coordinate. So, this is our current element, this. Now, let us say this is our y axis, this is our x axis, this is our z axis, and in this 3 dimension we will plot S average. So, that thing So, suppose this thing actually is a 3 dimensional thing, I have put a cut across this red line. So, it looks like this, that means cross section of this looks like this. So, what is S average here? Actually, the S average values we are putting here. What is theta? Suppose this point. Suppose I am talking of this point. What is the value of S average? This length is S average. So, you see at various points this is taking different values. Similarly, here what is S average? This distance is S average. Here what is S average? This distance is S average. Here what is S average? This distance is the S average. Now, the question is that where it will be minimum and what is theta? You see in this coordinate system, this is theta. When I am talking of this point, this is my theta. When I am talking of this point, this is my theta. Okay? So, obviously, it is having a maximum at theta is equal to 90 degree, because this point is the theta is equal to 90 degree, and it is having a minimum at 0. So, that means it shows that along the direction of the current element where the current is flowing, there is no radiation, you see, and it is having a maximum at a broadside to this antenna. That means, this antenna is a line 90 degree to that, this side, every side on this line there is a, that means, if this is a line, here is maximum, here is maximum, here is maximum, and also you can see that this whole thing actually, if we look at this expression, S average does not have any variation with phi. That means that along azimuthal direction there is no variation. So, that is why it is uniform. This shape is called Duff-Nut shape, Duff-Nut. So, you have that there is a this thing, if you revolve 360 degree you get a Duff-Nut shape, but it is difficult to visualize. So, what we do generally, this type of pattern, 3 dimensional pattern, we plot it as 2 dimensional patterns. So, what is a 2 dimensional pattern? Let us say that I am taking only the ZY, if I take only the ZY plane. So, there so what is ZY plane? Definitely I have put some value of phi. So, this is called fixed phi, that is why this is also called phi plane pattern. So, a phi plane pattern is dumbbell, current elements phi plane pattern is a dumbbell, maximum here it is a sin square theta variation. Similarly, another 2 dimensional thing will be if I fix the theta. So, fixed theta means you consider that if I fix the theta, it will be a xz plane fixed theta, and there the pattern will be something like a circle. So, at any point if I want to find what is the value of S average, this is the value of S average, you see always it is same. So, this is a theta plane pattern. So, power patterns of antennas are like this. It shows that in the azimuthal plane a current element does not have any variation, it behaves like an omnidirectional antenna, but in a phi plane it behaves like a dumbbell. So, it has in this direction it is giving more power than another direction, and at the current element line or axis it is having no radiation. So, now can you explain why this is so? Because the E field and H field both have a sin theta variation. So, E field and H field does not exist along this line. Actually, that is why vector potential exists along this line, because vector potential is cross product of magnetic field. Okay. So, this power pattern is a simple visualization of how effectively antenna puts its radiation in a particular direction. That means, I have said at the beginning of the class that antenna has two things. One is how much power it is able to put, that means how good impedance matching it is doing with the free space, how much power it is putting, and another is how directed it can make its beam. Now, this pattern, power pattern, shows us visualization of how directed it is, and we will do the next calculation for how much energy it is putting, how efficient it is. So, both these are terms efficiency, one is how directed it is and how much power it can put. So, next we will do that what is the total power that this current element is putting to free space, that means what is the total amount of radiation taking place. So, for that what we can do, we have already seen that S average, this the time average power density, that is solely directed in radial direction. We have seen that if we have a current element here, the radiation is taking place only in radial direction. So, what is the total of this radiation taking place? It is, we can think that we will have a spherical surface enclosing this, a closed spherical surface if we enclosing this current element, and then if we integrate this S average there, because it will come out of this area. So, over the whole surface area of the sphere, if we can integrate, we will get the total power, exactly we will do that. So, we can say that total power radiated, that will be a closed surface is so I can see that this drawing is something like this. I have the current element here and this is z axis and I am having an radius. So, that is r, and on this there is a ds vector. We know this value of ds vector in case of spherical coordinate, it is radially directed and its value is r square sin theta d theta d phi. So, we can put that, do this integration and it. So, I can write this, that S average will be, already we have found eta naught by 8 dl by lambda naught square I square sin square theta by r square. This is AR vector dot, this ds vector is r square sin theta d theta d phi AR, and how I wrote d theta means 0 to pi integration, d phi means 0 to 2 pi integration. So, if I do this, then let me go to the next page. I can find that this will be 2 pi eta naught by 3 dl by lambda naught square watt. So, radiation intensity integrated. So, total radiated power is this. Now, so from here actually if I call that I by root 2, I will call it as I RMS because it is a sinusoidal power. So, in that terms I can write it as I RMS square, and the whole rest thing you see power is equal to I square. So, who is missing R? So, that is called a radiation resistance. So, radiation resistance of an antenna, in this case this value is nothing but 2 pi eta naught by 3 dl by lambda naught square. So, if you manipulate, because eta naught value we know 120 pi. So, from that it comes 80 pi square dl by lambda naught whole square. Now, what is radiation resistance? That means, if I want more radiation, if I want a more efficient antenna means more period. More period means whatever I am giving is in my hand here, but how much it is sending, that is given by this. So, more R rad means more efficient antenna. So, this R rad is called radiation resistance. Now, actually we can say that as if instead of an antenna I have a fictitious resistance, I am giving IRMS current and power is dissipated here. In case of antenna, power is radiated. So, it is radiation resistance is a fictitious resistance that dissipates the same amount of power as that radiated by the Hertzian dipole or any antenna when both carry the same value of RMS current. So, more R rad better. Remember, this is not a circuit theory where we do not want resistance to be high, because that is the dissipation of energy, that is not useful. But in this case it is radiation. So, more radiation we want from antenna, because its job is to pump more and more power as much it can give. Whatever I am giving, I want 100% should be given. So, more it can give, that is better. So, radiation resistance higher is better in this case, but if I, so this is the performance measure of an antenna, for that how much power it can radiate. And already I have seen the directed nature, that was given by power pattern. Radiation resistance give the how much it can give, and how this Hertzian dipole performs. It is very poor in its performance, because if we just calculate the radiation resistance of thing, suppose I have, so for current element or Hertzian dipole, let us calculate. Suppose I have a 1 centimeter Hertzian dipole, that means my dl is 1 centimeter, and I want to radiate let us say 1 watt of power. At which frequency, that is important. Let us say f is 10 megahertz. So, I want to transmit 1 watt. 1 watt of power is sizable RF power. So, at 10 megahertz 1 watt power, if I give, actually the in cellular base station etc., they even 1 watt of power also they do not give, they give 200, 300 milliwatt power. But I am considering, suppose I use an current element and in a cellular base station I want to give 1 watt of power at 10 megahertz. Let us calculate 10 megahertz. So, its lambda naught, that will be 30 meter. So, R rad, that will be 80 pi square is roughly 10, you can say, and 0.01 meter, and it is 30 square. So, that will come to be 87.5 micro ohm, a very poor that. So, if I want to radiate 1 watt of power, how much current I will have to give? The current I will have to give, if we calculate just by I square R. So, what is the RMS current? I will have to give 106.87 ampere RMS current. You see, it is a huge RF current, 106 ampere. We cannot think, actually the current element may burn also from this. Now, instead of this, suppose I want to redo this, the same one, but I change the frequency to 100 kilohertz. The same conditions, 1 centimeter current element, 1 watt of power I want to transmit. So, find out what is the radiation resistance. Radiation resistance will turn out to be 8.75. Previously it was micro ohm, now it is nano ohm, and IRMS required will be 10.7 kilo ampere. Previously it was 100 some ampere, now 10.7 kilo ampere. So, you see, is practically there is no use for this. But this also, this exercise showed us one more thing. You see that why in the next case, that means in previous case I have this much, it was also inefficient, but next case it became much more inefficient. Just I have decreased the frequency, that means I increase the lambda. If I increase the lambda, then the electrical length of the current element got decreased in this case, and it became much more inefficient. So, that means the more electrical length of an antenna is, it is more efficient. So, this is an important thing, true of all antennas, that more electrical length of the antenna. What is electrical length? The length by lambda naught. So, if I can have more and more of this, then the antenna becomes efficient. So, the same current element, if I operate at 1 gigahertz, it will be efficient, but then it will not be a current element. Remember that suppose I operate it at 10 gigahertz, 10 gigahertz means 3 centimeter. The current element itself, its DL is 1 centimeter. So, the size of current element is lambda naught by 3, that we cannot call a current element. We will see that that becomes a familiar very efficient antenna near to that, that is a dipole, monopole, etc. So, this is an important thing, that DL by lambda naught, this size being small, current element is a very inefficient antenna. But then the question is that, also let me say another thing of this, that if we again look at the far field expressions of the current element, and let me write E far field as J some constant, let us say E naught, this is the shape, this is the field. So, you see this is some constant, but this is coming from, as we have seen, that this is solution of wave equation. So, e to the power minus j k naught r by r, this comes whenever I have any AC current. So, actually this is the genesis of spherical waves. So, in a wire if I have a current, varying current, I will get the far field will be of this. And what is H far field? Now, previously I have written, now I just want to say that I can also write it in terms of E far field. You look at the expression and I can write it as E far field. You see that takes care of its direction, because it is A theta, that will be A phi. So, A r cross A theta, that will give me A phi, but this is a general relation. Similarly, this E far field also now I can derive from the H far field, that E far field will be minus eta naught. This minus is coming because of the coordinate system, A r cross H far field. So, this is another way that H far field is A r cross E far field, E far field is A r cross H far field. This shows that E far field, H far field and A r means the direction of power flow, direction of wave, they are a right handed triplet. Now, that means something like plane wave. In plane wave also we have seen the same thing. The wave propagation direction, E field and H field, they are orthogonal. It shows that in the far field of an antenna, the electric field vector, magnetic field vector and the direction of wave propagation or direction of power flow, they are also forming a triplet. So, they are locally plane wave, but they are not strictly speaking plane wave, because if they are plane wave, this e to the power minus j k naught r by r term won't come. So, it is this divided by r that gives it a plane wave form, but at a sufficient distance locally over certain distance we can consider it as a plane wave. Now, this is true of all the antennas, though we have derived it only for this, but the people have derived it generally, that far fields of all the antennas have this type of structure. So, this is an important revelation, and from this we can also just find the far time domain expression of the far field. So, what will be the time domain value of far field? If I say instead of phasor, far field, that I can write just by, I will have to multiply e to the power j omega t, take the real part. So, by doing that I can write it as cos omega t minus k naught r. K naught r is coming from e to the power minus j k naught r, plus there is a j term, that is why it is j, and then a theta, and so this can be written as minus E naught by r sin. If we put k naught's value, we can write sin omega t minus r by c a theta, and H far field as minus E naught by eta naught r sin omega t minus r by c a r cross a theta. So, this also shows that in time domain the fields, they are delayed by a delay of r by c. That is obvious. If I have a current here, then it requires some time to go to this point, the fields does not reach immediately. So, this is the delay, that delay corresponds to the distance. So, from here r, and it propagates by velocity of light. So, wave that has a finite propagation time to reach a point instantaneously. So, this shows that actually the analysis of this current element has revealed many of the properties of the antenna which are not simple current elements, they are very complicated, some antennas, exotic performances, but the general structure of the fields are same, far fields are same, they always show there is a radial flow of power, there is a triplet, locally they are plane waves in the far field, they also have this time delay, they have the space delay according to the wave that created them e to the power minus j k r k naught r by r, and they have these all properties. That is why we studied current element. Current element is a very inefficient radiator. We will try to find that, but before that we have not answered one question, that is what is far field, because we have said it is far from the antenna that starts dominating. One thing we have derived that magnitude wise the far field becomes comparable to the induction field at a distance roughly r by lambda naught by 6, but is that the far field? So, in the next class we will say that for all antennas what is the criteria of far fields and what is the exact far field. Thank you.